Hello and welcome to the Cosmic Shambles Saturday Science Club. We're here every week with science and ideas, things that you can do at home with your family and things that you can try afterwards at home with your family, or even without your family if you want to have all the fun by yourself. So this is part of the Stay at Home Festival. Cosmic Shambles is doing loads of stuff while we're all stuck at home. And we're doing these every week. There's also science question and answer every Sunday. So that's tomorrow. And then lots of comedy and chat stuff during the week. So do go to the Cosmic Shambles website and have a look for all of that. All previous episodes of this are on YouTube. You can subscribe there if you'd like to. And very importantly, there is a tip jar, virtual tip jar, somewhere on the page you found this on. So it's on the Cosmic Shambles website. There's probably a link to it if you're finding us through other routes. If you're able to, and only if you're able to, if you fancy bunging £1 or £2 in the tip jar after this show or after any of our other shows, that goes directly to artists and performers and arts venues who are struggling through all of this. We've already made our first donations from that fund. They've gone to the Rondo Theatre in Bath, the Old Fire Station Arts Centre in Oxford, and the Little Angel Puppet Theatre in London. And we'll be making more donations this week. So that is a good thing to do if you fancy doing your good thing for the day. So we have so much today. We have hot chocolate and ice cream and stars and magic and mathematics and lots of bits and pieces. I'm going to get started, and I have something. So you can try this afterwards. It's probably quite slow to get going. You need a few bits and pieces. So I'm going to start off with my favorite mug. Now, this is my favorite mug. Firstly, because it's got all these eyes on it, which is just good. Now I've got a kettle of recently boiled water here. So this isn't really necessary for the demo, but I just wanted to show off my mug. Okay, so I now have I'm going to turn it around. A cup full of hot water, and you will see why this is my favorite mug, actually, because you can see that we're going from a nighttime ocean scene to a daytime one, and there's all kinds of fun squids and things in my mug. Anyway, that's not the science bit. The science bit is that over here I've got some, now this is hot chocolate powder because I'm a big hot chocolate enthusiast, and I see no reason why the arrival of nearly summer should stop me drinking hot chocolate. But it could be instant coffee or any kind of powdered stuff that you might put in a drink. So the first thing I'm going to do, I've not got enough hands here. It's going to take a bit of working out. Right, I'm going to hold it in that hand. So the critical thing here is what happens when you hit the bottom of the mug with a spoon. So it sounds like this. And the squid's very surprised. So now I'm going to stick in my hot chocolate powder and give it a bit of a stir. This is where it's probably going to get a bit messy, because normally I would put the hot chocolate powder down the bottom. But now I'm going to tap it again. And hopefully you can hear that not only has the sound changed, but it keeps changing as I keep tapping. So I'm going to give it another little stir. And you can hear the pitch is going up. So what's happening is you are hearing bubbles that are too small to see. And I'm always a fan of anything that involves bubbles. So when you add all the powder, you can try this with lots of different things. What the note is telling you when you hit the bottom, it's telling you about the sound speed in the mug. And when you add all that powder, the powder is quite irregular. It's got lots of little hollows, and it's got a rough surface, so it's carrying tiny little pockets of air, and those are bubbles. So when you stir it, you're stirring the bubbles into the liquid. So instead of being just water, it's now a bubbly liquid. And the thing is that slows down sound. So as I tap it, that's my test for how fast the sound is traveling. As soon as I put the bubbles in, the sound speed goes right down. It goes really low. So it takes longer for sound to go from the bottom to the top. So we hear a deeper note. And then as I keep tapping, the bubbles are rising out. So the sound speeds up, and the pitch goes up. So it's a great game to play. And I've now got hot chocolate to play with. So this is why I did it. This is why it's happening first. But it's well worth having a go. You can also sometimes hear a bit of a difference with different temperatures. So that's well worth having a play around with. Tap on the bottom of the mug, not the side. Okay, so there's a little bit of an experiment you can do at home afterwards. So we're going to move straight on from hot chocolate to the stars. We're going to start with Dr. Jen Gupta. She is a stargazer, astrophysicist. She's based at the University of Portsmouth. She is very enthusiastic about all sorts of things to do with astrophysics and the stars. And I think today she's going to talk to us about constellations. Off you go, Jen.
Cool, thanks Helen. Hi everyone. So as Helen said, my name's Jen and I'm an astronomer, and that means that I'm a scientist who studies stuff in space. And normally when I do these kind of talks, I'll have some pictures to show people either on a screen behind me or some big printouts of the kind of stuff that astronomers want to look at. And unfortunately, I don't have a screen behind me. All my pictures are locked up in my office in Portsmouth. And I was like, oh no, I've not got any pictures. And then I remembered I'm a massive space nerd. So what I do have at home is books like this. So this is Hubble, the Mirror on the Universe. And so I wanted to show you this one because yesterday was 30 years since the Hubble Space Telescope was launched. So Hubble has been in space for 30 years now. And this has got some lovely pictures in it of the kind of things that astronomers will observe. So some of you might recognize this planet. We like to look at planets. This is 5 images of the same one. That's Saturn. I am using little dinosaur stickers to mark my pages. Astronomers like to look at stars. Here's a nice picture of some stars in a cluster. And we like to observe galaxies. So here's a galaxy. A galaxy is a little bit like a star city. That galaxy I just showed you, the Whirlpool galaxy, a spiral galaxy, contains maybe 100,000 million stars, all held together by gravity. And I like to say that astronomy is simultaneously the most accessible and inaccessible science at the same time. Because on the one hand, when you think about it, as astronomers, as scientists, we can't do our experiments in the way that you would normally do your experiments here on Earth. If you do experiments at school, or maybe you've been doing some at home during this lockdown period, you get to poke things around, you get to test things out, you get to put meters into things and plug things in. But we can't do that with space. You know, I can't go to one of those stars I just showed you in that cluster and stick a thermometer in it to measure how hot it is. I can't go grab a bit of gas from that Whirlpool galaxy and bring it back and test it in a lab to see what it's made of. So we have to do our experiments in a little bit of a different way, and it can be a bit tough never being able to actually go and see it with our own eyes or you know, like actually be there in person. But at the same time, it's hugely accessible because everyone pretty much can be an astronomer. As long as you've got a useful level of vision, you can go out tonight and you can look up at the sky and you can see the stars, maybe the planet Venus if you're out early enough in the evening. You can see the moon at certain times of the month, and you can do astronomy. Even if you're vision impaired or you're blind, there are ways to do astronomy. A cheeky plug for one of the projects I'm involved with. This is a 3D printed little image of a galaxy. So we're making them so that you can feel the galaxy, you can run your finger over that instead of seeing it. And so people who are vision impaired and blind can participate in astronomy as well. You don't need binoculars or a telescope or any of that kind of kit to do astronomy, although it can help. And so I thought that I would spend a few minutes showing you some of the stuff that you can see in the night sky tonight and over the next few nights, because obviously we're all in lockdown, we're not meant to be going out too much. But what you can do is go into your back garden or your front doorstep, your balcony, even looking out the window, you'll be able to see some stars tonight. We're having some great weather at the moment, so it should be clear. And normally, again, I would do this in a huge inflatable planetarium. We'd be sitting inside, I'd be projecting the stars up, it would be wonderful, but I don't have that here. So instead, I've got a blackboard. I'm going to draw you some stars. I'm going to show you my skills of an artist. There's a little strong bad reference for anyone who was also an internet nerd in the early 2000s. And so I'm going to show you, start with a pattern of stars that is always my go-to, the first one that I go and look at. So let me see if I can draw this. I will make no claims that this is to scale, but that's about right. So a pattern of stars that looks a little bit like this. This is a picture, a pattern of stars that we call the plough. And so as astronomers, what we tend to do is imagine that there's lines connecting these stars together. And so this one we think looks a little bit like a saucepan with a bent handle. And it's a really good one, the plough, to spot when you go out at night, because from the UK, this is visible every single night, and it can help us to find our way around the night sky. And what I want to show you, what you can do is use it to find north. And so to do that, what we're going to do is imagine this is like the handle of your saucepan. You follow it round, go down to the pot, go across to these two stars over here. We're going to call these our guide stars. And if you measure the distance between those two stars as a step, and they go from the bottom of the saucepan to the top, and keep going up 5 steps in that direction. So we'll go 1, 2, 3, 4, 5. You end up with a star that's above my head somewhere. That star, if you find it from the plough, is the North Star. And so if you find it and then you draw the shortest line down to the ground, that direction is north. And so once you've found that, you can start to orientate yourself and figure out which direction you're looking in, which is really useful for stargazing. And so I did this last night. I went out about 10:30 last night, found the plough. It was nice and high above my head in the sky. I found the North Star. And then I swiveled round 180 degrees to look south, and I found another pattern of stars. And so this one is a constellation called Leo, and I'm not as good at drawing this one, so I apologise if it doesn't quite look right, but it basically looks a little bit like this. So you're looking for something that looks a bit like a backwards question mark over there, and then it goes out and along. So this is a constellation called Leo the Lion. Don't want to show it to you for any astrology reasons. I don't believe in all of that. But I wanted to show this to you because I actually tried to see it last week. Last week I went out one night because one of my friends texted me and was like, Jen, why is the sky moving? And I was like, wait, what? And I went outside and I looked up and I saw this line of dots, bright dots moving slowly across the sky. And they were going in front of this constellation. And they were so bright that actually the light from those dots kind of overwhelmed my eyes. And it meant I couldn't really see the fainter stars in this. God, I've drawn that really badly, in this constellation of Leo. And what those lights were the Starlink satellites. So these are satellites that are being sent up by SpaceX, Elon Musk's company. And the idea is that there'll be like 10,000 of them up in space, and they can beam high-speed internet down to rural areas, remote areas. And so that's a great idea, a really fantastic use of space applications of satellites. But there's unintended consequences. And particularly for us as professional astronomers, we're really worried because these satellites are so bright. As I said, they overwhelmed my eyes, so I couldn't see Leo behind it. They could ruin all the observations that our telescopes can do. Imagine that you've got a huge telescope on top of a mountain in the middle of nowhere. You're looking out for a planet in the outer parts of the solar system. People are looking for planets beyond Neptune. And while you're doing that, you've got these really bright satellites going into your field of view of your telescope. That's going to ruin your observations. And I think that SpaceX, they didn't necessarily think about this and consult astronomers before they started putting all these satellites up. There are conversations going on now. And so if you go out and look for them, and it is a cool thing to go and look for, it's always nice to see satellites. I would just urge you to have a little bit of a think about the kind of wider implications and the bigger context that those satellites are being put in. So I'm going to stop there. Enjoy the rest of the show. Stay safe, everyone, and I'll see you again soon.
Well, just before you go, Jen, first of all, I love your necklace. If you're at home, notice Jen's necklace and have a think about what it is. It is something you'll recognise once you spot it. Especially
it's actually it's a teething necklace that I got custom made for my daughter.
So if you can't work out what it is, ask us on Twitter towards the end, and we'll let you know. So Jen, what you, apart from looking up at the sky in general, are there particular places that you think people should go if they fancy a bit of stargazing during this period? Where can they go?
I mean, physically stay put, but a great app that I've got loaded on my phone. I don't know if you'll be able to see that. This is an app called Stellarium, and it's glaring quite a bit, but it you load it up on your phone, you put in your location, and it shows you what you're looking at. You can set it to any time, any location. So that's showing me what I'll see at 16 minutes past 10 tonight from my back garden. So there's loads of these kind of apps that people can use to help them navigate around the sky. I have to admit, I don't know the majority of the constellations up there, so I always check something like Stellarium. If people want to get involved with science, some people watching may already know about the Zooniverse platform, citizen science platforms. There's loads of projects out there like Galaxy Zoo, where you can look at pictures of galaxies and tell us what they look like, and you're helping people do their research. So if anyone's bored with an internet connection at home, I'd urge you to check Zooniverse out.
Brilliant. And there is so much on this. So I've got a second flag wave here. For if you're interested in old ship logs or in stars or in penguins, you can help with a little bit of science. So definitely go to that website. Jen, thank you so much.
Thanks for having me.
And send us a picture of your necklace so that we can put on Twitter and people can see if they guess what it is. Okay, we are going to move on from the stars to ice cream, which is clearly the best thing, going from my hot chocolate to ice cream. So for this, we have Professor Andrea Sella. He's a colleague of mine at University College London. He is a big enthusiast for all things related to chemistry. He is normally to be found either creating a mess or making something explode, and quite frequently both. We should all be glad that we are not in the same room as Andrea, because when he's doing something interesting, it is almost always better to be some distance away. So the other end of an internet connection is perfect. Andrea, what have you got for us?
Well, look, you know what? I'm deeply, deeply offended, because this is the one time when you really want to be in the same room as me. Because, what I want to do is to explore an interesting question. And that is, we all love ice cream. But one of the real questions is, ice cream is not something new, right? People have been eating ice cream for 200, 300, 400 years, possibly more than that. And the question is, how on earth did people manage to do that back then? Now, what I'm going to do is this is going to be a little bit tricky, because I thought I would have an assistant with the camera, but I'm on my own. But what I've done is I've got a whole setup here on my son's bedroom table. And in front, I think you can see that I've got a temperature display. Now, can I just ask, is it coming out the right way around? Can you read the temperature in this room?
Yes, we're fine, Andrea.
It's okay, yeah. Because on my screen it comes out backwards, and so I'm horribly confused. Now, this is what's called a thermocouple based thermometer, and you can see this little tip here, and that's actually the junction between two different kinds of wire. And when you join two pieces of wire, it makes a voltage, and that voltage depends on temperature. So if what I do is I press this between my fingers, you'll be able to tell that I'm alive, right? I'm not just a robot, right? My body is warm. Of course, my fingers are not a really good way to measure my body temperature. So, my fingers are always a little bit colder. If I were to stick this in my mouth or something, shall we try that? Let's go and see if that's a little warmer. So we'll now just, And now I think you can see, right, right, that clearly, right, there's a temperature difference between my fingers, right, on the one hand, and my mouth, and that's why you normally measure, a kind of deep body temperature. Okay, so if we want to make ice cream, how are we going to do it? Well, what I've done is I've actually got myself some ice, and you can see that I froze loads of ice cubes. I've got them in this wine cooler here, and this wine cooler, notice, is really clever because it's double glazed, right? It's insulated, and this is what scientists call a Dewar flask. And here's an actual sort of lab Dewar flask that I'm holding in my hands, right? And you can see that in the lab we use very, very similar kinds of glassware. Now, what I'm going to do is I'm going to put some ice into this beaker, and I want you to keep an eye on the temperature. So let's just put the thermometer in there. We'll take some of this ice, okay, and we'll drop it into the whole thing. And now, notice that the temperature drops immediately. Let's put a little water in there. Not too much, just a bit. And we have the thermometer actually sitting in the water. The water is a little warmer, but if we stir it for a second, we should see the whole thing drop down. Now, what temperature are we expecting? Well, I'm sure you're all shouting, 0 degrees, 0 degrees. And that's where I think we might end up if all goes well. But it takes a moment, because we also have to cool the glass down and so on. Anyway, we're at about 0. Now, that isn't going to be cold enough to be able to make ice cream. So how are we going to get the temperature lower? And I want you to think back about 200 years, say, before refrigerators were invented. How could one achieve lower temperatures? And the answer is this stuff. Okay? What I've got is a bunch of table salt here. And what I'm going to do is I'm just going to pour it in the top. Pour it in the top. And I want you to watch what happens to the temperature as I stir it. As if by magic, the temperature has dropped, and it's dropping steadily, right? It's going down, down, down. And in fact, if we keep stirring this around, you can see that the temperature is just getting lower and lower and lower. And this is really, really bizarre. Because if you think about it, if you mix two things together, what you'll normally get is kind of the average temperature between them. So if you take hot water and cold water and you mix them together, then what you should end up with is something kind of in the middle. And yet here we've added warm salt. And what we've seen is that adding warm salt to this ice and water mixture is actually causing us to cool down. And this is very, very strange indeed. I mean, you can see the temperature is really low. I mean, this is, we can carry on down. We're at -8 degrees now. So we've already dropped by about 11 degrees, since I put the salt in there. And if we keep stirring, we'll be able to go lower and lower and lower. So the question is, right, what's going on here? And it's worth kind of thinking about this. So let me just stare at you, make a little bit more kind of eye contact. But there's something really interesting, and that is that if we think about what happens when you have ice and you have water, right, there's a boundary between them. There's the edge of the ice. And when the ice and the water are at 0 degrees, right, when we're actually at that melting temperature, then you have the same number of water molecules leaving the ice, melting. And in fact, you can see them dripping off my hand, right, because the ice is in fact melting. But the water that's at 0 degrees, there will be an equal number of waters going in the opposite direction and sticking to the ice. And so when you're at 0 degrees, you're at this perfect balance point. It's what we call equilibrium. And that's what we call the melting temperature. That's where you have equal numbers melting, equal numbers freezing. Now, the interesting thing is, what happens when you add the salt? Well, when you add the salt, what you do is you don't change the ice at all. The ice, it's a solid, so it's not going to mix in. But on the other hand, the salt is going to dissolve in the water. And as it does so, it gets in the way of the water molecules that are trying to land back on the ice. And the result is that the ice keeps melting. But to break the bonds in the ice, you need energy. And the only place to get that is by cooling the ice. And so everything continues to cool down so long as you have that imbalance. And eventually you're going to get to a temperature where everything comes back to equilibrium again. So I have a challenge for you. If you have an indoor-outdoor thermometer, or thermometer which has this kind of little probe that you can dip into water and salt, then you have a challenge to see how cold you can actually get something. What is the lowest possible temperature that you can get? Now, this is something we do in the wintertime. We put salt on the road. Why? Because what it does is it lowers the temperature, right, for the melting. And so that means that any slippery ice on the road will melt away, and you'll be left just with a wet pavement. That's a lot less slippery than an icy one. But our temperature has gone down quite a bit. We've gone down to -7. And now I think we should think about trying to make ice cream, okay? Temperature is actually down at -9. So there's a really simple way to do it. What I want you to do is to get yourselves some freezer bags, okay? And into these freezer bags, you want to put some crushed ice. So I'm going to take a little bit of ice and I'm just going to smash it, okay? And there's a reason for this, because I want lots of surface area. Okay, so I've just broken it up. We've got a big mess here on the table. My son will probably be quite irritated, but there we are. Okay, so we've put it into the outer bag. And now what we'll do is we'll take the inner bag. This is going to be the inner bag. And into this, I'm actually going to take my custard. Now, how do you make custard for ice cream? It's really easy. All I did this morning was I took about a mug, 2 mugs full of milk. I put in an egg yolk and some sugar, and then I put them on the hob, and I just warmed them up and stirred them quite a lot. I think I've put in a bit too much here. I may struggle to freeze that much in the time available, so let me just pour it back out. Sooner or later, there's going to be an enormous, the enormous mess that Helen is cheering for, right? Okay, so I'm almost there. So now we have to zip the top up. And now we'll put it inside the other bag. And now the final thing is to add salt. Now wait a second, be really careful. You want to put the salt into the outer bag, otherwise the whole thing will end up tasting disgusting, right? So it's in the outer bag. And now what we do is we start smushing it all up. Start smushing it all up, and we know that the temperature is going to start to fall. And in fact, this bag is getting really quite cold. It might be worth actually wearing gloves as you do this, okay? But what's going to happen is the whole thing's going to cool down, and within about 5 minutes or so, we'll have ice cream. So what I'm going to do, I think, is I'm going to hand you back to Helen. I'm going to carry on smushing for a bit, and then at the next break, I'll try and jump in for a moment and tell you, A, show you whether it's turned into ice cream, but B, because you're not here, right? And Helen did tell you that she didn't want to be in the same room as me. Maybe I'll get to taste it. Let's just see. Yeah, it's thickening up, but it needs a couple more minutes. So back to you, Helen.
Thank you, Andrea. One thing to note, if you're going to try that at home, definitely don't put your fingers in it. That mixture. Andrea, can you use your microphone? Definitely don't put your fingers in that mixture of ice and salt, because that's not good for your fingers, those kind of temperatures. However, that is how they made ice cream. We'll go back to Andrea after our next guest and see how he's getting on. And our next guest is a maths enthusiast. She gives loads of talks and does demonstrations, all involved, all around thinking about maths, using it in the real world. And I think she's got some magic tricks for us, with showing us the magic of maths. This is Zoe Griffiths. Oh, Zoe, you with us? Zoe might not be with us quite yet. Oh no, maybe we've almost got her now. Okay, so in between, so while we're waiting for Zoe to turn her microphone on, I'm going to tell you a little bit about the science Q&A that we're doing tomorrow. So on Sunday afternoons, we do there's a Cosmic Shambles Stay at Home Fest Science Q&A, and tomorrow it's going to be me and Robin Ince and Matthew Cobb and Brian Cox, and we'll be answering your science questions. We welcome questions on any area of science from anyone. So as young or as old as you are, anything that's been bugging you in your head, do send it into Cosmic Shambles. And at 3 p.m. tomorrow, we'll be answering your science questions live. However, we are now back with Zoe for some maths magic. Zoe, what have you got to show us?
Okay, as Helen said, my name's Zoe. I'm a mathematician, and I'm here to show you some mathematical magic tricks. So these are tricks that you can work out kind of how and why they work by using mathematical thinking, and that's what you're going to do. So I'm going to show you to try and work out why these tricks work. And so my first trick, I'll be using these giant cards, and I'll also be making it really obvious what it is that I'm doing in the trick. There's no sleight of hand, nothing dodgy going on. I'm literally just following an algorithm to make this trick work. So I'm following a set of instructions, and if you follow the same instructions at home later on when you try this trick, then it'll work for you too. So watch carefully. Our first job is to make 3 piles of cards, and there are 3 cards in each pile. So 1, 2, 3 here, 1, 2, 3 here, 1, 2, 3 there we go. And the next step is to ask your volunteer to choose one of the 3 piles. Now Helen is my volunteer. So Helen, would you like pile 1, pile 2, or pile 3?
I would like pile 2, please.
Pile 2, okay, so that's this one here. So I'm going to pick up the pile that Helen chose, and I'm going to show the underside of it, so the card underneath, to the camera. Now I can't see my video feed, that's not how this trick works, but in case you don't believe me, I'm going to shut my eyes. So there we go. So this is your card, Helen, and everybody at home, that's your card. Have a good look. Okay, so don't forget your card. Once you've done that, pick up the pile that your friend chose and put it on top of the other 2 piles, like that. There we go. And now the position of your friend's card in the pack is 3rd from top, because it's the bottom of the top pile. And the next thing to do is to ask your friend to lie about the card they just saw. So to say the name of any other card. So Helen saw, please.
It was the 2 of clubs.
It was the 2 of clubs. Oh, okay, so we've all just seen the 2 of clubs. So what I'm going to do is I'm going to spell out 2 of clubs. And every time I say a letter, I'm going to put a card onto the table. And when we get to the end of the word, we'll pick up those cards, put them underneath. And at the end of the whole phrase, 2 of clubs, we'll see where Helen's card has moved to in the pack. So T, you can do the spelling at home with me if you'd like to. W-O, when we get to the end of the word, we pick up that word and put it underneath. Then of is O, and then F. Oh, well done for not saying a second F, that would be off, excellent. So that then goes underneath, and then clubs is C, L, U, B, and then S, stick those underneath. And now the amazing thing about this trick is that whatever card phrase they say, however long it is, as long as it's a real card phrase, the card that they chose at the beginning will always end up in the pack. This is amazing, right? This is the magic. We're going to see it happen in a second. But first of all, I have to remind myself that Helen is lying to me. It's okay. I told her to lie to me. That's fine. And so therefore, 2 of clubs is false. And false is spelt F-A-L-S. And so every single time, amazingly, whatever card phrase they say, the E of false will be their card. So hopefully that's your card, Helen?
It is, yes.
Oh, amazing.
Brilliant.
Great stuff. So we can do this trick again. Helen could choose a different card phrase and it would still work. The only rule is that you don't choose Joker. So that doesn't count. Otherwise, any card phrase, it will work. And it's your job at home to try and work out why this works. There's a number of different things you can do to investigate that. So I'm going to move on to my second trick, which doesn't involve cards, but does involve a calculator. And so Helen's got a calculator with her, I think. And so I'd like Helen to type in. You've got a calculator? Perfect.
I have just picked it up, yeah. Type
in any 4 into your calculator. Any 4-digit number at all.
Okay.
And then I'm going to ask you to mix that up a bit. So I'd like you to press plus, and then 17. So 17.
Okay.
Plus 17. And then press equals.
Yep.
And so now you've got a new number on your screen, hopefully. I know you can add 17 in your head, but there is more coming. So you've got a new number in your screen, and you're going to mix up a little bit more. So you're going to press multiply by, and then let's do 18. So 18.
Okay.
And then press equals.
Yeah.
So now Helen's got an even bigger number on her screen, and I'd like Helen to write down that number on a piece of paper, nice and big. And she's also going to choose one of her digits from her calculator display to be her secret digit. And I'll explain what that means in a bit. But she can choose any one of those numbers from her calculator display to be the secret digit, as long as it's not a 0. So it needs to be a non-zero secret digit, Helen.
Okay.
And you can indicate to the audience which number is your secret digit by circling it. So you can circle your secret digit.
Are we ready for us? Can I show everyone?
You ready? So what I'll do, actually, Helen, in the same way that I can't see my video feed, I also can't see Helen. But in case you're not convinced of that, I'm going to shut my eyes again. So I tell you what, I'll count down from 3, and on 0, if you hold up the piece of paper, and if you say done when you're done, I'll know I can open my eyes. So 3, 2, 1, 0.
Here we go. Okay, done.
You're done. Okay, so I can open my eyes. Excellent. So you've all just seen Helen's numbers. I haven't seen them remember what 4 digits she started with. But despite that, in a second, she is going to read out all of her digits apart from her secret digits. And just by reading her mind, I am going to tell her which digit she missed out. Are you ready, Helen? Go for it.
Okay, so the non-special numbers are 2, 7, 3, and 2.
2, 7, 3, and 2. Helen, I think you missed out a 4. Am I right?
You are right. Yes, Yay. There we go.
Amazing. Oh, thank you. I can hear you all applauding at home. Thank you very much. Excellent stuff. So magicians don't always reveal their secrets, and it's your job at home again to try and work out how I did this trick. But I will give you one clue. So although I've got no idea what 4 digits Helen started with, I do have some information about the number she ended up with. Because in particular, I know that her final step was to multiply by 18. And there's a number of different things we can say about the answer we get when we take a whole number and we multiply it by 18. Like, for example, we know that the answer must be even. You can go and have a think about why that must be true. But there's lots of other facts that are true about the answer that we get. And it's one of those other facts that allows me to do this trick. So lots to think about there. This is on YouTube, so you can watch it all again, get the again, and see if you can work out why they work. That's me done, so thank you very much for watching.
Brilliant, thank you, Zoe. And just very, very quickly before you go, if people are in need of some extra maths entertainment in the next few days, is there anything in particular you'd recommend?
So there's a website called mathematicalmagic.com. Very easy, just www.mathematicalmagic, no spaces, no dashes, no dots or anything, .com, which has got videos of all sorts of different tricks that use mathematics to make them work. And similar to this, they'll show you the trick and you've got to try and think about why it works. So definitely go and have a look at that website if you're interested to see more.
Fabulous. Thank you very much, Zoe. Who doesn't want a little bit of extra magic in their morning? And we are going to go back to Andrea, who has now made ice cream in some chemistry magic. Andrea, how's your ice cream? What's it look like and how's it taste?
Okay, so let me just, as you expected, Helen, and that is that one of my bags, the outer bag, sprung a leak. And so we've got a bit of a salty mess on the floor. But let's look at the temperature. What I've done is I actually put the inner bag into the beaker that I had before. And you can see the temperature is at -11. And if you look at what's coming out of the bag, the stuff is really quite stiff. And so what I'm going to do is I'm going to open up and I'm just going to scoop out a nice little bit of, actually it's still a little bit on the sloppy side. But what I've got here is some rather nice, very nice sweet vanilla ice cream as made by me a little while ago. So all you need is a bit of salt and a bit of ice, and then you just need some bags, right, so that you can keep the salt away from your custard, and ice cream is yours.
That is fabulous. Thank you so much, Andrea. So if you've ever wondered how to make ice cream without a freezer, there you go. Now you know, and highly recommended. It looks like we're coming into summer. So if you can't go out to get ice cream supplies, you might be able to make your own at home. So we are going to finish with a song from Jonny Berliner. However, just before we finish, I've got a few last things to tell you. Of course, we'll be back next week with more guests, more demos, more things to try at home. So do be back at 11 a.m. next Saturday to join us. The tip jar is somewhere. There'll be a link somewhere down here on the Cosmic Shambles website. So do put a £1 or £2 in that if you would like to help us support artists and performers and arts venues who are having a tough time while we're all stuck at home. It is very important to keep the cultural aspects of all of our lives going. So if you can do that for them, we'd really appreciate it. You can subscribe on YouTube to these videos. All the previous week's science clubs are all up, and you can have a look. This one will be up in a couple of hours, so you can look at the whole archive. Subscribe to the Cosmic Shambles channel there. Tomorrow we will be having our regular Sunday question and answer session, science Q&A. So that'll be Robin Ince and me, and tomorrow we also have Brian Cox and Matthew Cobb. I nearly got the surnames the wrong way around then. Both start with CO. So yes, Matthew Cobb and Brian Cox. So we'll be answering your science questions on anything and everything. So if you've got something that's been bugging you, one of those questions that has been hiding away down the back of the sofa of your mind, and you just wonder why is it that happens, send it in, send it to Cosmic Shambles via Twitter or Facebook or email, and we will do our best to answer your questions. So that's 3 p.m. tomorrow. We'll be live. And now to finish off, we have Jonny Berliner, the physics teacher with a guitar. He has all kinds of songs about physics on his website. There's lots of homeschooling stuff there too. There's a website called www.scitunes.org. So if you'd like some extra physics and song and worksheets to go with it, lots of physics things to think about, that's the place to go. But to play us out, here is Jonny Berliner with a song about forces, I think. See you next week.
If you're an engineer designing cars or planes, how do you know that when they use they're gonna be safe?
You can make a prediction that's so precise it's insane, with equations, calculations, and imagination.
What will you need to know?
Speed, distance, mass, and time.
What are they?
Scalar quantities that only have size, but some quantities are vectors with direction besides. That's how velocity, acceleration, and force are defined.
But what's a force?
Push or pull,
like magnetism and weight.
they are the ones that can't still pull when the objects separate. But compression and tension and their resistance relate. Their contact forces
Like a normal force and friction.
Add them together to treat them like there's one. I use resultant forces to predict the outcome.
Push it.
Change your shape, your speed, or your direction.
Pull it.
When forces balance, you won't change momentum.
Push it.
Force is mass times acceleration.
I will pull or push you back in every situation. Tell me what you know about gravity.
Bigger, closer things pull more attractively. Define the weight, multiply the mass by G. The field strength on Earth is roughly 10 newtons per kilo.
And if I'm stretching a spring,
Physics law to see that the tension and extension go proportionally.
then what's a moment?
Turning force like spanners need. Force times distance from the pivot perpendicularly.
Okay, but how do forces link with something's energy?
Force times the distance moved is work that's done mechanically. It's the energy shifted between stars. An example could be shifting by lifting to be stored in things gravitationally.
So what's momentum?
Mass times velocity. And if it's slow, then something's motion changes easily with
Push it.
change your shape, your speed, or your direction.
Pull it.
When force is balanced, you won't change momentum.
Push it.
Force is mass times acceleration.
I will pull or push you back in every situation. I want to drive fast. How fast can I go?
That depends if you've enough stopping distance to slow.
Why?
You need time to react, which may take longer, you know. If you are tired or if you're drinking alcohol.
But I can stop really
But
fast.
then the force is felt can cause internal damage.
Even with a safety belt.
And since brakes will dissipate energy, that's how they'll be squared. stronger to stop when driving fast. Push it. Change your shape, your speed, or your direction. Pull it. When force is balanced, you won't change momentum. Push it. Force is mass times acceleration. I will pull or push you back in every situation. Push it. Change your shape, your speed, or your direction. Pull it. Force is balanced, you won't change momentum. Push it. Force is mass times acceleration. I will pull or push you back in every situation. Oh.